labs not have any roads. And real world.
That's what was wrong for me.
Yeah. Real doesn't have any indications. It doesn't have
It's okay. Not the arguing setup.
All right. How's everyone doing today? Cool. What's up?
I understood like what I was doing.
Oh, wonderful. Okay. Before we get started, any questions on labs? Okay. I got a couple emails about this over the weekend. So when you're putting your lab reports, make sure you include like a paragraph in there about, what you were doing in the lab. It's a requirement. There's points for it. So just make sure you do that. Anything else? Okay, cool. So we're going to be working on our lab 4 this week, and we're going to be doing a 2D braced frame. So it's like the frame we did last week, except instead of having moment connections being the sole means of translating the lateral forces down the structure to the foundation, we've got some bracing members. So those are usually some diagonal members in some of the bays. So we're going to consider a 2D braced frame shown in figure 1. It's going to have 3 bays, each spaced at 12 feet, and 3 stories, each at 12 feet. And we're going to consider the self-weight of the structure to be present. So pretty similar to last week. Dimensions are a little different. We're going to be using Kipp's feet in Fahrenheit. We're going to be using steel. We're going to be using W16 by 77 beams, W18 by 97 columns, and 8 by 8 by 1/2 angles as our braces. And we're also going to be showing you how to do some load combinations. So we're going to have a couple different types of loads on our structures. So dead loads, live loads, wind loads. I hope by this point you've looked into kind of different types of loads and load combinations in your various other structural design classes. Like I think you all should be in steel design at least by now, right? Oh, right, they moved that. Have you guys covered the different types of loads and load combinations and stuff yet? Okay, well, we'll go over it. So we'll do that, and then we've got some deliverables. So here is the structure we're going to be analyzing this week. Sorry, let me zoom out. I got this computer really zoomed in here. Gosh. Okay, so we have 3 bays across, 3 stories tall. And in our center bays here, we have these bracing members, these diagonal members here. And these are called eccentric bracing. So they're eccentric because they don't go and cross the bay. If they make like an X across the bay, it's called concentric bracing. But because there's a bit of a gap between these, they're called eccentric. Sometimes if they meet right in the middle, it's called a K brace or a chevron brace as well. But this one we're doing today is an eccentric brace. And like I was saying, we go and throw in these braces here to help take these lateral loads here and bring them down to the foundation. So it's not just through the tension and compression in these members. So it's not just the moment connections doing all the work there. And we have some dimensioning here to show that there's a bit of a gap between these here. Do you guys have any idea why we might want to have a gap between the braces here?
I'll be at like 1.
I'm sorry?
Be all 1 joint.
It would be if they all meet at one point. And that's desirable in some circumstances. In other circumstances, we could use one like this. So in this case, what we can do here is we can actually go and free up some space architecturally in this bay here by not having it go all the way across and basically block off that whole wall all the way up and down the building. So if you need to be able to get through here, that's a good solution for that. So a compromise you can make with the kind of functional need of the building here. Though a lot of the times they'll go and put like braces somewhere in the core area, like behind the elevators or next to the stairs or way on the ends of the building. So it's not quite as much of a concern. But if you need a brace somewhere and you still need people getting through, this is a good one here. And another benefit of this is that this little bit in the middle here, it's this little beam between the braces here, it's sometimes called a fuse. This can be a good detail for some seismic design. It can, the way these would deform, that would absorb a lot of energy there. And it's a nice controlled way to control how your building responds seismically. So that's very advanced design stuff. If you're very interested in that, we can get into that in advanced steel design and more graduate level classes. But some concepts that you might want to know the very basic premise for here, a use for this type of bracing here. So any questions before we get started? Okay, cool. So let's get SAP up and running, and then we can start modeling our structure. So while SAP's getting up and going, let's talk about load combinations. So load combinations are how we go and combine the different types of loads acting on our building. So far, we've just been using everything as a dead load. What's a dead load? That's a load that's always present on your building. So like the self-weight of the structure, like all the partition walls and stuff in the building, stuff like that. All the furniture. Live loads, that's loads that can enter and leave the building. So that's like all the people in the building. That can be like, if you've got like a library and stuff, they go and move those books around sometimes. So those can be considered live loads. So if it's like a storage place, like all the weight of the items they're storing in there could be live loads. So stuff that can enter and leave the building, basically. And then we've also got other types of loads throughout the building, like wind loads, seismic loads, snow loads, rain ponding loads. There's loads from the earth if it's bearing against the building, like on the footings or on the foundation walls or something like that. It's called lateral earth pressure. If you're building a dam or something, that's called hydrostatic pressure. I'm sure you'll know about that from fluids, I hope. So there's all sorts of different types of loads acting on our building. Now, when we're designing our building to make sure it handles all the loads, we go and find the maximum amount of load we want it to handle in all those cases. We can pull that from a code like ASCE7. And if we go and just say, hey, I need it to withstand all this dead load, all this live load, all this snow load, all this earthquake load, all this wind load, everything all at once, that'll work. But if we're designing it to take the maximum amount of snow that we could predict it's ever going to want, and the biggest earthquake that it's ever going to have, and the heaviest it's ever going to be with the most people in it all at the same time, we're really going to over-design that building. Probabilistically, that's almost never going to happen. It's like vanishingly small that the odds are that all that load's going to be in there. So how do we give ourselves a little more economy with that? We go and use load combinations like this. So in ASCE 7, we have a whole bunch of these. There's like 5 normal ones and then some more for lateral loads. And what we do is we go and plug in all of our loads into these equations and see which one gives us the highest load combination. Then we design to that combination. And these factors in front, like 1.2, 1.6, 0.5, 0.9, 1.0, those are tuned based off of probabilistic models and performance data from existing buildings. Then a lot of work's gone into that. So those are pretty good factors for figuring out, what's going to give us a good building life based off of the loads we'll expect to get it with a very high probability. I think the return period on these is like 2,700 years between loads that we'd expect to exceed the load combinations here. So pretty good. Does that help explain that a little? Okay, cool. Yeah, and then we have the dead loads and live loads here. And those correspond to the loads we have in our figure. So let's get our model going. We're going to create a new model. It'll think for a second. First things first, units. So kips, feet, and Fahrenheit. And then we're going to be wanting to use a 2D frames template here. So we'll click on the 2D frames here. Now, if you remember last week, we left this as portal frame. What we can do now is we can click on the eccentric braced option here. So that will give us these eccentric ones. In your assignment, I think I gave you a concentric one, which has these X's here. So that's a little easier. So just be aware there's that difference there. So for this one, we're going to be using eccentric. For your homework, use concentric. And now we've got some options here. We have even spacing in our stories and bays. So we can use the boxes at the top and we don't need to create a custom grid spacing. So we'll have 3 stories, 3 bays. Each of those will be 12 feet. And then the gap width here, that is going to be 3 feet as dimensioned here. So we'll put in 3 for our gap width. Okay. So these should all be 3, and then those should both be 12. Now, we will want to import our beams and columns and our brace. So this is just like we've been importing sections before, except now instead of everything's going to be one type of shape, we're going to assign different shapes to different parts of the building. So the beams are going to be one, columns are going to be another, and the braces are going to be another. And those will be these ones right here. So first things first, let's hit our plus button, import a new property. First, let's do our beam. So that's going to be a I/wide flange. So click on that. We'll scroll down to AISC15 and open that. And then we'll scroll down to W16 by 77. Click on that. And then we can press OK. And then OK. And we've got our first one in there. Now, once we've done that, we can import our other 2 while we're in here as well. So we'll click this again. Our second one's going to be another I/wide flange. So let's click on that. Because we went and used AISC 15, the last time it's gone and brought that up again, which is fine because we don't need to pick another database for it because this one should be in there as well. And we're going to pick W18 by 97. So we'll go down to the W18s, click on 97, click OK, and then OK. Now I've got both of these. And we want our third and last shape. So we'll click on import new property again. And the brace that we want is an angle. So an L 8 by 8 by 1/2. So we're going to click on the angle shape right here. And then we're going to scroll down to the L 8 by 8s. And it's going to be nearly at the bottom. So L 8 by 8 by 1/2. And then we'll press OK. And then OK. And we should have all of our shapes in our properties here. Any questions on that? Yeah. You could do that, yeah. So what you'd do is you'd still go and import all your sections. You'd go and highlight the ones you want to apply your section to. And then you'll go to assign frame sections and then pick the section you want to have it applied to. Okay, so press OK here. And now we see in our box down here, we've got beams, columns, and braces are all set to W16 by 77. So we can look in the dropdown and it'll have all those properties we imported. Beams are supposed to be W16s, so that's good. Columns, we're going to switch that to a W18 by 97. And the braces here, we're going to switch that to the L8 by 8 by 1/2. Make sense? Okay, and then last, we're going to uncheck restraints here because we want it to be fixed, and this will give us a pinned connection by default. So see, we want fixed. This will give us pinned, so I uncheck that so I remember. Then we'll press OK. And we've got our frame. So first things first, let's do those restraints. So we're going to go assign, joint, restraints, fixed. Okay. So now we've got our fixed restraints there. Okay, cool. And our geometry should be done. So if we want to double check what all of our members are, we could go up to display and then go through these menus like I showed you last time. There's another option that we can do through one of these buttons here, and it's called set display options. And this gives you just a whole lot of check marks to be able to show a whole bunch of things on your model. So it's little check mark blocks up in there. And to go and show what our frame sections are, we can go to frames here and click on sections. So click on that so it's checked, and then press OK. And we can see our section designation for all our frames there. So we see all of our beams are those W16 by 77s, all of our braces are those angles, and all of our columns are those W18 by 97s. And if we get tired of that, we can either hit the show undeformed shape here. Oops, that doesn't do anything. So what we can do is go back to that check mark box and uncheck sections, then press OK again. So that's a real nice way to go and change your view of what's all on screen sometimes as well. Okay, any questions on that? So that's all of our geometry that we need to do. So next we want to apply our loads. So first thing we need to do is we need to set up our different types of loads. So previously we've just used dead load, and that comes as a default load case with all of our models. Now we need to set up a live load and a wind load for the live loads and the wind loads that will be applied to the building. So to do that, we go to define, and then we'll go to load pattern. And you might remember, hey, this is where we went to turn off the self-weight before. It's also where we go to add different types of loads. So what we're going to do is we're going to create a new type of load. We're going to call it a live load. And then in this drop down here, we're going to click on live load. And by default, the self-weight multiplier is 0. And then when we're done with that, we can say add new load pattern. So we'll click that, and it's added the live load to our table down here. And we're going to do the same thing again for wind load. So we're going to click on, call it wind. We're going to click on wind in our list here. It's also going to have a self-weight multiplier of 0. And we're going to see that in an auto lateral load pattern here, we have this thing pop up by default. We're going to set this to none, because if you don't, it's going to generate a whole bunch of different types of wind load patterns there. Why does it do this? Well, normally when you're designing a structure, you've got wind, and it's not only coming from a single direction. So you have to analyze it for wind coming in all these different directions. So that tool goes and makes all those different types of wind loads, but automatically. However, for this one, we only just want the one wind load. So we'll do this. So it should say wind, wind, 0, none. Then we'll add it to our load pattern, and it should look like this. Make sense? Cool. So now that we've got that, we can press OK. And we need to do one more thing first. We need to set up our load combinations. So we'll go to define, and then we'll go down to load combinations. And this is where we go and set up those load combinations that are factored combinations of different types of loads. So we'll click on add new combo. You can name it. I like it. automatically names it combination 1, so I just keep that usually. And down here, we go and select the type of load we want to include. So we've got dead, live, and wind. Ignore modal, that's a dynamic type of load. Well, we don't need that. So we've got dead here, the type of addition here, and the scale factor. So we want our scale factor for load combination 1 to be 1.2. And then we click add. Then we'll click on live, and we want that scale factor to be 1.6. And then for wind, we want that scale factor to be 0.5. And that is this load combination 1 right here. That's given in the worksheet. And I just know all those because I use it too much. Okay, so once we've done all that, we can press OK, and we have combination 1. Now we want our second combination, so I'll say add new combination. And we notice that we now have combination 1 in this list as well. So we can make combinations of combinations if we wanted to. We're not going to do that today, but it's an option if you want it. So we'll click on dead load. We'll set that factor to 0.9. And then we'll click on our wind load and set that factor to 1.0. So our combination 2 should look like that. We'll press OK there. So now we've got our 2 combinations. And now we can press OK. So all of our kind of load preparation work is done now. So let's go and start adding the loads. So we're going to have dead loads as distributed loads on all 3 of our floors, live loads as distributed loads on all 3 of our floors, and then our wind loads are these 15, 30, and 45 kip point loads on the edge of the building here. And then our dead loads are going to be 10 kips per foot, and those live loads will have 15 kips per foot capacity or magnitudes. So let's go and select my beams here. And then we can go to assign, frame loads, distributed. Now we're doing dead loads, and now we need to start paying attention to some things in the top box here. So the first thing is the load pattern, and this is where we select what type of load it is. So it's on dead by default, so we'll keep it that one for this one. And then dead loads are going to be 10 kips per foot. So we'll put in 10 in the uniform load box here. And then we'll press OK. So now we have 10 kip per foot dead loads on all of our floors. And we can do the same thing again for our live loads. Yeah. I'm sorry? An error in assigning. Sounds interesting. Okay. So just a reminder from last week, make sure you're using your classic plus graphics mode because we're assigning distributed loads in a 2D view for whatever. Go to options, go to graphics mode, and click on classics plus. Yeah, sure. Yeah, no worries. So if your program crashes, just save it real quick and then open it back up. Well, in this instance, it hasn't technically crashed. It's just that the graphics stopped working. The program's still running in the background. It's just not updating the picture, which is kind of weird, but such are bugs. So when we get around to doing it, we'll do the same thing again, but for live loads, and then we'll go and apply our point loads as wind loads. Any questions in the meantime?
Why is it on the diagram that we give it says dead load and live load on the sides, but in the middle it just says live?
Good catch, because I wasn't looking at it very closely. So I added some loads on these by accident. So now's a good time to show you how to unload something. So I accidentally added dead loads to these middle ones. So let's select them. Let's go to assign. Let's go to frame loads. Let's go to distributed. We have a dead load there that we don't want. So this one's on dead. Set it from 10 back to 0. Click OK. And now they should be gone. Good catch. Thank you.
They're not supposed to be.
Dead loads are not. Sorry, I didn't quite read that. So we've got live loads on all the bays, but dead loads on just the outer bays there. Not sure why it's set up like that, just to be tricky, I guess. Okay, cool. The live loads will be 15 kips per foot, but the dead loads that we just added were 10. Okay, ready to go? Okay, so we're gonna move on now. So once we have our dead loads just on the outer base here, let's add live loads on all of them. So we can select all of them this time. And then we're going to go to assign frame loads distributed. Now this time, instead of dead up here, we're going to click on live. And then in uniform load here, we're going to press 15. And then we'll press OK. Now we have 15 kip per foot live loads on all of our beams here. And if we're ever wondering, okay, what type of load am I looking at? If you look on the tab up here, it should tell you we're looking at live loads. And you see it's only live loads. It's not going to display live loads and dead loads at the same time, because that would be confusing to some people. If you right click on a member and go up to loads here, you can see all of the different types of loads that are applied to it on a member by member basis this way. If you're just curious to make sure it's still there. It's AutoCAD rules for dragging.
Yeah.
Drag right is inclusion, drag left is anything it's touching. Yeah.
Nice. Yeah, no, I usually for the.
I mean, technically you should, but in this case, no.
That's why it's selected.
Okay. So we've got our distributed loads now. Let's add our point loads. So those will be 15, 30, and 45. So let's click here. Let's go to assign joint load forces. Now up here, instead of dead, we're going to click on wind. It's going to be a horizontal load. So that's going to be in the force global X direction. And that's going to be 15 kips. Press OK there. We've got our 15 kip wind load there. Select the next one up. Assign joint load forces. This one's still on wind. Change that to 30. Press OK there. And then last one up, go to assign joint load forces. Change that to 45. And we're good. So we had a good point brought up here. A lot of the time when we're using braced frames like this, it's because we aren't necessarily detailing all of these connections to be full moment connections. So we would want to add some releases in there. For the simplicity in this lab, because we're already introducing a bunch of other stuff, just leave it all as is. But when you're actually practicing, it is more pinned than fixed a lot of the times when we're using braces like this. Actually, most connections are more pinned than fixed when they're detailed, and usually they'll call out connections on plans if they're supposed to be a moment connection. But for now, well, because moment connections take a lot more time to put together. But for now, we're just gonna keep it all rigid for today. Okay, so we've got everything assigned now, so we should be good to run our analysis. We're gonna turn off modal, and we want to make sure dead, live, and wind are all running, because if they don't, our load combinations won't run because they need all three of them to run the combination. And we'll press run now, and it'll want us to save it, so we'll do that. And it'll take a second, and we see it deforms a bit. Little spaghetti looking there. So this is the dead load. And if you recall, that's had these distributed loads on these outer bays here. So it makes sense that those are kind of all getting deformed like that. And it's kind of deforming the rest of the structure in response to that. Okay, so let's look at our deliverables. Everyone get something that kind of looks like this for their dead load? No? Uh-oh. Yeah. What happened with yours? It tilted? Okay.
Let's take a look.
Well, you know what happens? We don't have any boundary conditions. Make sure you put your fixed conditions on the bottom, otherwise the computer thinks what's happening, and this thing just went and fell like 1,000,000 miles. So you're gonna have to really get this plane on that. Make sure you add your boundary conditions. Fixed at the bottom. Yes. And then make sure you have fixed boundary conditions. You have to.
Yeah.
Okay, sorry about that. So we've got our frames here. Now for our deliverables. Everyone good to look at these? Okay, so we're going to look at our reactions first. So to do that, we're going to go to display, show forces, stresses, joints. And we want to look at the reactions for load combination 1. So by default, it's dead load. But now if you look in this dropdown, we have dead load, live load, wind load, and both of those load combinations we defined. So we're going to click on load combination 1 here, and then press OK. And we've got a whole bunch of reaction values down here. So we see we've got our X and Y reactions, or sorry, our X and Z reactions and the moments. And if I look at it in 3D here, we've also got the Y and the Y reaction and Y moment as well. So if you, when you're taking your screenshot of these, just the ones in this view here are fine. Make sense? Okay, so reactions, same as usual. Except, make sure you're getting the reactions for the right type of load or load combination here. Next, we want to look at the deformed shape for load combination 2. So before we were looking at the deformed shape for the dead load. Now let's look at the deformed shape, but for load combination 2. So in our display deformed shape menu here, we want to look at load combination 2. And then I'll turn on wire shadow, and then we can press OK. And it should look something like this. So in load combination 2, we had 0.9 times the dead load, and then all of our wind load. So it should be kind of shifting over like our portal frame last week, except if you look at the actual deflection values, it's going to be a lot smaller. Yeah, so 0.03 feet instead of, 1.3 feet. Yes. For our story drift values, yeah, just one for each level. So that's the next load combination. Sorry, so that's the next deliverable here. We want the story drift values. Take them from the right bay. It'll get you the values most consistent with the ones I use in my solutions. For load combination 1, do it again for load combination 2. And then I want the ratio of the drift from combination 2 to combination 1 for each of the floors. So in your report, usually you should have 9 values. You should have the drift value for the first floor, second floor, the third floor in combination 1. Well, this one's 2. We'll go and look at it again for load combination 1 here. Go and take the U1 value here, here, and here. So that's 6 of those values. And then using those, go and take the drift value for the first floor from combination 2, and then divide it by the drift value for the first floor from combination 1. And that'll be your ratio for this floor. And then do that for all 3 floors. So you should have 9 values in your report. Usually a nice table's easy to keep it all organized in there. Yes.
I'm actually wondering which value.
U1. So U1 is our X displacement of that node. So drift is in the horizontal direction, which is X here.
So that would be
U1. Yeah. Is there a question over here? Okay, thought I saw a hand. So does that make sense what I'm looking for the drift values and the ratios of them? So drift is our X displacement. This gives you your displacements in X, Y, and Z, so 1, 2, and 3. Drift, when I'm talking about that in 2D, that's going to be U1. Yeah, so just the U1. I don't want all of the displacement values.
Do you have a preference for which load combination is on the divider? Like
2 on top, 1 on bottom.
2 is the greater?
Yeah. Yeah, so when you do this, your ratios should be about 2 or so. Make sure you're doing it right. If it's a half, flip them. Or something went really wrong.
I'm looking for that. So think of it in terms of like, oh, when I have this, these are 2 cases, right?
Yes.
The way that the load combination is like case 1, case 2, and then do you think about it in terms of like case 2 is 2 times case 1, or is it opposite, or is it just
so in load combination 2, we're accounting for all of the wind force that gives you your lateral deflection. In load case 1, we're usually only accounting for about half of it. So in case 2, it should be about twice what it is in from combination 1. But you've got different amounts of vertical force, so that'll mess up the numbers a little bit. It should be around 2, but I'm looking for the actual numbers that you guys should find from it. But yeah, in that ballpark. Yeah.
We do the ratio for each story.
Exactly. So you'll have one from combination one from combination two, and a ratio for each story. So that's 9 numbers in total. Cool. Make sense? Awesome. Okay, so last two, we want the shear diagram, and we're going to look for the value of the max shear in the second story column for load combination 2. So our shear diagram, we'll go to frames, cables, tendons, go to load combination 2 here, and shear 2, and show values. So those are normal. Make sure we put it on combination 2 here, so that's the one we want to look for. Press OK. And we've got our shear diagrams. And we're glad that the computer does it for us. We can click on object shrink toggle here, make it a little more legible. As we can see, there's very small amounts of shear in our braces here, so that's good. Those are kind of slender. And then these 4 right here are our second story columns. So let's just take a look, see what our maximum shear is in those. So we got 15.5 here, 1.5, 18.2, and -0.5 here. So maximum shear we need to design for is 18.2 kips in these columns here. Make sense? Cool. And then lastly, our moment diagram, same procedure. Let's double check which combination we wanted this for. Again, for load combination 2, and we want the same ones in the second story columns. So instead of shear 2, we'll click moment 3, press OK. And here are our moment diagrams. As you can see, lots of fun there. So it should look like that. So you can use object shrink toggle to break up the diagrams a little bit. And then let's look for our maximum moment in these columns. So our max moment in this one's -12.5. Our max moment in this one is -109.4. In this one, it's going to be -16. And in this one, it's going to be -95. So 109.44 here in this beam here. That's going to be our max moment that we need to design for. Make sense to everyone? Okay, so make sure you include your screenshots of all the shear diagrams here, as well as let me know that what your max moment is. Same for shear diagrams. Include each of the story drifts for load combination 1, combination 2, and their ratios. So that's 9 numbers in total. You know, your displaced shape and your reactions. And when you're doing them, make sure they're for the right combination that I'm asking for, because there's 2 of them. So make sure it's the right one. Okay, any questions? If not, thanks for coming, and we'll see you in class on Thursday.
Just
See ya.
For the lab,